Okay, look at question 22 is almost the same like question 21. The rate of decomposition of a radioactive substance is directly proportional to the amount of substance. Write a differential equation which describes this phenomena by taking n as the amount of substance at time t and k as the constant of proportion. That means like this. Okay, the amount is like this. If you look at the graph, the amount is n and this one is t. Okay, so the amount n. Okay, so that means at time t the amount is n. But what is the original one? After we read and see. Okay, here they say, here decompose means the mass loss decrease. Here increase 0 because we don't add in the substance. So the decrease one, the rate is proportional. Proportional to what? Proportional to the amount of substance. So amount of substance is n. So same like just now, dn dt proportional negative n. You must put negative, don't forget this side is negative, this side is positive, because this side add in, this side is lost. And then negative kn like this, then we integrate. Okay, then this is the differential equation they ask us to write. This is called the differential equation. Okay, they ask us to use n. Question number 22. Okay, then the half-life T of this radioactive substance. What is half-life? Half-life means the time for half of the substance to be decomposed. That is the half-life. It's defined as the time that lapses before half of the amount decomposes. Find an expression of K in terms of T. That means you see, because at the beginning, you look at the graph here. What is the mass at the beginning? Okay, let's say m. We have to assume m. Half-life means t is the half-life. That means after the time t, we have half remain. That means the starting one is m, half of it remain. That means another half already decomposes. So this is half m, and then the time is t. So here, this is for us to find the c. This is for us to find the k. That's why you see I substitute. I integrate first, and then like just now, I substitute t equal to 0, n equal to m, I get the c. This is my c. Okay, then I substitute c inside here. I substitute the c inside here to get a particular solution. And then here, I substitute. Okay, I simplify it first, and then finally I get n equal to this. And then I will substitute t equal to t, this one is for us to find the k, as I said earlier. Okay, so I substitute, then I get this is the k. So you are asked to show that the k is equal to this, is it? Here they say find an expression for k in terms of t. So we have got it. Okay, the radioactive substance has an initial radioactive level of 1 curie and a half-life is 10 days. Okay, now the time is days. Find the percentage of the radioactive substance remain after 100 days. That means here they say the initial amount is 1 curie. That means this one starting is 1 curie. That is our m. So m is 1. And then the half-life, just now the half-life t is 10 days. So the big T is 10. So we substitute into our equation just now. So we have n equal to m. M is 1 here. We substitute here 1 exponential negative k. And then k is 1 over t ln 2. So we substitute inside 1 over 10 because t is 10. 1 over 10 ln 2 and then t. So substitute here from here. Okay? Because the k is this. Okay, we put in everything here. As I get n, the m is 1, the k is 1 over t, which is 10 ln 2, and then t. So that's why I get this. So I simplify, I get this. Okay, now we want to find the amount after the percentage of the radioactive substance remain after 100 days. So for after 100 days, After 100 days, we just substitute t equal to 100. So when I substitute t equal to 100, I get 0. So I get so many curie. So how many percent remain? 0.00198 divided by 1 times 100, because the beginning one is 1 curie. Then I get 0.098 remain percentage. Okay. Then the last part, part B. The minimum lifespan of the radioactive substances, if it can be disposed of only after the radioactive level has reduced less than 10 to the power negative 4 curie. That means this one, the radioactive substances, we have to keep it until the radioactive level is less than this one, then only is safe to throw away. If not, it will affect our human body. Is it? So you see, at first is 1 curie. That means this radioactive level is too high, so we cannot dispose because this is harmful to our body. So we have to wait until less than 10 to the power negative 4, then we can throw away. That means after this time, it's safe to throw away. Okay, the radioactive level is safe. Okay, so here you see, given n smaller than this one, then it is safe to throw, to dispose. So we just substitute like just now, n equal to, this is 1, like just now the equation here, we substitute back into this equation, and then we want to find the t, isn't it? Now the n we substitute. So we know n should be smaller than, okay, this is our n, and then we know the n should be smaller, the amount should be smaller than 10 to the power negative 4, then it is safe. So n substitute smaller than 10 to the power negative 4. So we just solve here, use your calculator or what, use your calculator to solve this. Okay, then you get this. Afterward, finally you get t more than this, and then okay, then you get this one, the t is more than 132.9 days. This should be days. So that means you have to keep for 133 days, and then only you can throw away. Okay,